Hello, I've had a couple of questions about the floating point homework I set last week. So in this video, I'm going to try and go through question 9, and I'll attempt to do something similar for question 10 as well, if that's helpful. So how do we approach these kind of questions? Well, you read them through carefully first. A real binary number may be represented in normalized floating point binary notation with 5 bits for the mantissa and then 3 bits for the exponent, both in 2's complement binary. Okay, so we have 5 bits for the mantissa first. 1, 2, 3, 4, 5. 3 bits left over, so that's the 5 bits for the mantissa. 3 bits left over for the exponent, 0, 1, 1. I would start with the exponent first. We know it's positive because we have a 0. We know the mantissa is positive because we have a 0 as the most significant bit. And then we've got 1, 2, minus 4 because it's 2's complement here. 1 plus 2 is 3. So if it's clear from your working that you've got 0, 1, 1 as your exponent, and that's 3, you get 1 mark. For the mantissa, we need to work out what this is if it had an exponent of 0, because we can only work it out if we assume the exponent is 0. So to get from an exponent of 3 down to 0, we have to decrease the exponent by 3. So if we're decreasing the exponent to balance out the values, we have to increase the mantissa. What does that mean? So if this is 0.1100, to make it more significant, we have to make each of the bits more significant by moving the decimal place 3 spaces. Why 3? Because the exponent is 3. So we're left with 0110.0. This was a positive number. So this 0 is insignificant, we can ignore that. So we're left with, so this bit above here would be worth 1, 2, 4, that would be worth a half. We can ignore the 1 and the half, and we're left with 4 plus 2 equals 6. Okay, so things to remember here is if you increase the exponent, you have to decrease the mantissa and vice versa. And if you want to be able to convert to denary, you have to make sure that the exponent goes to 0, so you shift the mantissa accordingly. Let's do the same kind of thing here. It's a bit more complex because we're working with negative numbers. So 5 bits for the mantissa, 1, 2, 3, 4, 5, first 5 bits here. 3 bits for the exponent. 3 ones is minus 1. You can either just remember that all of the ones is minus 1, or you can do 1 plus 2, take away 4, and you're left with minus 1. Or you can flip the bits and add 1 and make it negative. Both of those methods give you minus 1. Okay, so let's do the same kind of thing. If we start with the decimal place just after the first digit, then we need to increase the exponent to 0. And if we're increasing the exponent, we have to decrease the mantissa, which means all of the bits have to become less significant. We do that by moving the decimal place over to the left or moving all of the bits to the right. That's why I avoid talking about shifting to the left or to the right, because I'm never sure whether you're talking about shifting the decimal place or shifting the digits. I think it's helpful to talk about increasing the exponent, so I'm decreasing the value of the mantissa so that they balance. Okay, we've got to be careful here. This is a negative number, so it's equivalent to being padded with 1s on here, just as if it was a positive number, it would be the same as padding it with 0s for the most significant bit. So that means we have to put a 1 in here, not a 0. So this is now 1.101. We need to work out what that is. It could be minus 1 plus a half plus not a quarter but add an eighth, or we could flip the bits and add 1, which is what I'm going to do. So we're going to do 0.010. We need to remember to add 1, so that becomes a 1. So what have we got here? We have got a quarter and an eighth. Add those together, make sure they're minus. So a quarter is 2/8, add 1/8 equals, and we have to remember that that's all minus, the end result is 3/8, minus 3/8. So the last one is slightly different. We start with a denary number this time, 3.5. So we can do this in fixed point. So we start with a decimal place. The 3 is just binary 3, but we have to make sure we've got a 0 in front to tell us that it's a negative number. And then the 0.5, well, 0.5 is a half, so it's just going to be a 1. And then as many zeros as we like, doesn't really matter. We have to normalize it. So we need to put the decimal place, so remember you can pad with as many zeros as you like before. We need to put the decimal place after the first time where it changes, and it changes here because we know it's a positive number. So we're shifting across 2 spaces to be left with 0.111, and then as many zeros as we need. And in the format described above, the mantissa had 5 bits, so I'm going to take one of those bits there, so we've got 5 bits there. So that's the mantissa sorted, 0, 1, 1, 1, 0. The exponent, well, we had to shift 2 places in that direction. So here, from our normalized mantissa, we want to make the bits more significant, and in order to do that, we would have to have an exponent that is positive of 2. So does that make sense? Yeah, have I got that right? Yeah, okay. So what is the exponent as binary? So 2 as 3 bits, 2's complement is going to be 0, 1, 0. So the final result is going to be 0, 1, 1, 1, 0. That's the mantissa, and then 0, 1, 0 for the exponent. Okay, hope that's helpful. Give me a shout if you've got any questions or if you want any more practice examples to work through.